So thank you very much for having me. It's an honor to be here. There we go. Excellent. Thank you so much for having me. It really is a privilege to be here. I want to talk today primarily about flooding and flood forecasting. And I'll talk about that because that's kind of primarily my domain, though of course there are many exciting opportunities for AI in other water management areas. But I want to maybe first highlight that even just within flood management, there is a lot of impact and a lot of progress to be had. Floods are the most common and one of the most deadly natural disasters on the planet, affecting hundreds of millions of people, causing tens of thousands of fatalities and around $10 billion in economic damages. But on the bright side, they're also one of the natural disasters where we can most effectively mitigate the harms. Lots of research here, you can see one of them shows that we can really significantly improve both reaction and protection and preparation for floods using early warning systems and reduce as well fatalities and other harms. In fact, flood management is so effective that the World Bank, in collaboration with the UN and several other organizations, found that early warning systems more broadly are the most cost-effective adaptation-related intervention that it recommends. And these numbers are far larger, specifically in flood forecasting systems, and specifically those in low-resource countries, where cost-benefit ratios can be as high as 500 in multiple countries. And because of all of this, that's kind of the reason why we started the Google Flood Forecasting Initiative, which aims to provide accurate and actionable flood alerts covering anyone who's affected by floods globally, with a current focus on riverine flooding. So that'll also be a bit of a focus in my talk, whereas still, of course, flash flooding and coastal flooding are also incredibly important. But what I want to do today is talk about AI-driven innovations in flood forecasting, some of them done by my own teams, some of them elsewhere. There's a lot of exciting progress in recent years and a lot more to be done. And since there's a lot to talk about, this will also be a bit of a whirlwind tour. So I'm going to kind of rush through a lot of different opportunities and developments, but I'll make sure to include references at the bottom of the slide. So if anyone wants to deep dive into any of these topics, you're more than welcome to. Broadly, you can see here a somewhat simple division of flood forecasting systems and their components. Three key parts of them are one kind of hydrologic models, which accept as inputs precipitation and other weather forecasts and provide a forecast for river conditions, whether that's discharge or water levels. A second important component is, or sometimes separate, sometimes not, but I'll be referring to them separately as inundation models, which given expected conditions in the river, simulate how water is going to move across the floodplain to provide more spatially accurate and actionable forecasts for what will happen. And then a final important component is, of course, making sure that that information reaches the people that it needs to reach, whether those are governmental stakeholders, NGOs, or of course, directly the people who are affected. Today, I'm going to talk about primarily the first component. I'm going to talk a bit about inundation modeling as well. And because we're focused on AI, I'm not going to talk about as much about warning distribution. So the hydrologic model I just mentioned, kind of the first forecasting component, or the first one in kind of really in flood modeling. Of course, it'll rely on inputs on models of weather and things like that. And before I talk about innovations in the actual modeling, I want to talk a bit about really exciting development in recent years that have enabled advances in AI and in all data-driven modeling. In recent years, there's really been huge progress on large-scale hydrologic data sets, including CAMELS, HISETs, GSIM, and so on. And I want to specifically highlight what is, I think, the latest and largest data set, Caravan, which combines all previous open large-scale data sets and also allows for different people to add their own data. So this data set is actually continuously growing as more people add data on their own. And really, these data sets have been critical in allowing us to make progress in the kind of data-hungry types of models that we'll be talking about here. The first thing I want to mention is kind of the actual hydrologic model itself. The classic hydrologic modeling approach, right, is through physics-based or even conceptual models where we try to explicitly model the different specific processes that occur throughout the basin. But as I'm sure many people here are aware, there are a lot of challenges with these models. They often end up being over-parameterized relative to the amount of data that we have in a specific basin, especially in data-poor regions. And they also require a lot of manual calibration, which is expensive and hard to scale, right? That's why countries spend enormous amounts on flood forecasting systems per river, and countries that can't afford that will often not have the state-of-the-art in hydrologic modeling. I think one of the most exciting developments in recent years have been the ML-based, machine learning-based approach, and specifically led by LSTMs, which are a specific neural network dedicated to modeling time series, and specifically time series with long time dependencies. And I want to share maybe one graph from one paper. This is one of the many papers in recent years benchmarking these new LSTMs relative to classical hydrologic models. This graph is slightly confusing. I'll take a minute to explain it. What we're seeing here, each line represents a different model. And you can see here a bunch of models that I'm sure many of you are familiar with: HBV, VIC, the Sacramento model, and so on. And each line shows us the performance of that model across hundreds and hundreds of different basins. This specific graph is from a paper on the continental United States, but there are many others in other regions. And what you're seeing is really the distribution of different scores, specifically Nash Sutcliffe efficiency scores, across these hundreds of basins throughout the United States. And really what you need to know is that lower in this graph is better. It means that the model is getting higher scores on more and more basins. And now I just want to add there kind of the results that we're now getting from LSTMs, which we can see is a really major leap relative to what we've seen across classical models before. Now, this paper is not the only one to show this. There's many. I want to maybe mention one more, and that is often a response to this kind of improvement in metrics is that these machine learning models will improve on the metrics that you can measure, but maybe screw up on the measures that you can't measure, right? That there's these things that are hard to quantify that maybe we're losing on the way. This is a study that we did kind of asking more than 600 hydrologists in academia, industry, and the public sector to manually inspect hydrographs of different models and say which they think is performing better. And you can see here that the LSTM-based models vastly exceeded the performance relative to all other benchmark models, even when this is manual evaluation by humans. As a side note, we also found that almost all hydrologists claim that they can see things that the metrics don't capture, that there's some kind of things that are hard to quantify. But if you try to take a hydrologist's estimate of the quality of the hydrograph, that is a worse predictor of what other hydrologists will say than a fairly simple combination of the NSE and KGE metrics that many of us are familiar with. Moving on, there's been, I think, another challenge often, a true challenge with AI-based systems is that we are sometimes paying a price with interpretability, right? Maybe it performs better, but we don't understand why it performs better. And that's troubling for a lot of decision-making considerations. Recent work by Chao Peng and his group have shown that you can get almost state-of-the-art results, almost match the results of LSTMs, really very, very small differences in quality, but combine them with classic models, in this case using HBV, and get all the same set of variables that you need for interpretability and understanding what is the underlying process driving this without sacrificing a significant amount of the accuracy. So I think this is a really exciting result, adding robustness and kind of being able to use these results in a wider range of scenarios. There's been some really exciting work also on uncertainty estimation. I think we're all used to using ensembles for during kind of giving a full distribution of results. But ensembles, it's very hard to properly calibrate them, right? There's no explicit way in which we can require them to be more calibrated. We just kind of have to play around and maybe add fixes until we get something that's good. And they're also computationally expensive, right? We need to run things many, many times. There's been really exciting work on explicit modeling of the distribution. So this is, again, using neural networks to just produce the parameters of the distribution of the output. And here specifically, I'm kind of highlighting a paper that used what's called a countable mixture of asymmetric Laplacians, which is similar to maybe the more famous Gaussian mixture models that maybe some of you have heard of. But this has been optimized specifically for hydrologic uses where often your uncertainty is highly asymmetric. So Gaussians, again, you could with enough Gaussians, but you need tons of data. CMOLs are actually kind of inherently asymmetric and can support this much, much better. And we've seen great results both relative to ensembles and to other machine learning-based methods. And these things are not just in the lab, they're not just in academia, they have been deployed operationally at a large scale. Just to, again, share our results, even though, again, there are many other teams doing exciting work here. Just in the year 2021, we've launched these systems across hundreds and hundreds of different basins with really, really exciting results. Here I'm showing the results for the actual operational system. So that this is not our evaluations prior to launching. This is the actual alerts that we ended up sending out. And we had a R squared, in this case, it's over water levels of 97% and an average error of 8.5 centimeters. Now, of course, as all of you know, this will be very different across different basins. So in some sense, these numbers are telling you more about the slow moving and easy to predict rivers where we've started. This slide doesn't mean to claim that all rivers in the world can be predicted to this accuracy, but it does show you that you can reach with these systems in an operational, real world setting, extremely high accuracies in many locations. I think a lot of what our focus has been in the last year, and I think a lot of other groups as well, has been on making these things available at a global scale. There's been, throughout recent decades, strong trade-offs between being able to predict accurately and being able to scale globally. And we're trying to overcome, and I think that machine learning and AI really is a key part of overcoming that challenge. And I won't have time to kind of really go into this architecture, but we have kind of new variations on these LSTMs that seem to perform extremely well across the world. And we've since run this in more than 1 million points across the world, across all significant basins globally, and benchmark this against everywhere where there are publicly available measurements. And this is still pending publication, so I won't have the numbers to share with you, but there are really exciting results against the leading global flood forecasting systems, where we expect really a leap in quality of forecasts globally over the next year or two. Okay, finally, I want to say just a few minutes on inundation modeling, an area that is also incredibly important in translating these forecasts into actually being actionable and allowing people to know whether they're in danger, what they want to do to address this. And here again, the classic kind of models are physics-based models, in these cases, kind of really pure end-to-end physics-based models, St. Venant equations and so on. That's kind of a very classic way of doing inundation modeling. And these can be incredibly accurate when you have all the data that you need, but really are sensitive to, let's say, the quality of elevation maps and are very computationally prohibitive, especially if you want to scale globally. A lot of the work that I think machine learning is doing these days in improving inundation modeling is helping them learn things that we don't know a priori. Even if we don't have the riverbed bathymetry, even if our elevation maps are not perfect, even if there are underground structures that we don't see, we want to be able to learn from experience, and machine learning models help with that. This starts with pure data-driven models, which we've shown are in many circumstances, and especially in data-scarce areas where we don't have high-quality elevation maps, are comparable to hydraulic models. Of course, those might have trouble generalizing, but once you do have data-driven models, you can incorporate information that is hard to incorporate otherwise. For example, our current models will also incorporate all the latest satellite imagery when assessing the current and future flooding situation. And we've been able to show that they produce even more accurate results, not only on average, but even for unprecedented events, simply because they can get the latest information and incorporate that in a way that's difficult. But of course, as with many areas, the most exciting results are when we combine this AI-based and the classic physics-based intelligence, right, that our models can encode and incorporate. I won't have time to get into it. Again, you can look at the references, but I think the manifold is a great example of taking the best of both worlds, combining some data-driven automated learning with a lot of physics-based insight to produce great results. And just to share with you an example of what that ends up looking like, this is a comparison between real-world forecasts. This is one example of flooding and what areas ended up being flooded. So of course, no forecast is ever perfect, but you can see here we can provide a lot of value, a lot of information to people on what areas are likely to be affected days in advance. Finally, I'll just say, here you can see an example, a real-world example as we were traveling to flood-affected areas, and you can see how the dot there shows that we are right at the edge of where we forecasted there would be flooding, and that isn't the case. And I really do think, this is what we should be thinking about as we do this work. AI is already playing a really big role in flood forecasting and water management right now, but I really do think we're just getting started with major advances still occurring every year, because it has the potential drive to, incredible progress that can translate directly into better lives for people across the world. I'm really excited about this space. So thank you all for listening.
Thank you so much, Sella Nevo from Google's Flood Forecasting Initiative. I would like to move now to our next keynote speaker. Joining us now is Nicolas Zimmer. He's the CEO of Technology Foundation Berlin. Nicolas Zimmer, welcome. Thank you so much for joining us today. Go for it.
Thank you, Jennifer. Thank you for having me. Probably everybody knows what Google is and does. Nobody knows what Technology Foundation does. So just a few introductory remarks about our institution. We are focused on digital transformation in and for Berlin, oriented on the public good, because we are a nonprofit organization. And we build on the concept of openness. So open information, open data, open source are the pillars of our work, which we do in different projects like Berlin City Lab, the Public Innovation Lab, which we operate for the Berlin Senate. And last but not least, we are also one of the two shareholders in KWB, Kompetenzzentrum Wasser Berlin, which is also one of our closer connections to the topic of water. So now I'm also jumping into my presentation. And what I want to do now is to give you a public perspective on artificial intelligence. And due to this title, you can expect some more general remarks. I hope you can see everything. And now we start. So, smart cities need smart water, needs artificial intelligence. That could probably be a wrap up for our topic today. If you're looking on it from the pundit's perspective, everything is clear, everything is cool. What's not to like about that? But as we are talking about a public perspective, when you ask people, the truth about smart cities is that people don't give, well, I don't want to have Jennifer now push the profanity button, but people actually don't care about smart cities as much as we all expect. What they care about is food and water, health, housing, and stuff like that. So the quality of living is what people are really interested in. They are not interested in large concepts, frameworks, plans, political discussions. They're interested in their concrete benefit. So the first remark I want to make is, please don't find solutions for problems that don't exist. Everything we do should be done with a clear and firm look on what benefits the people. This is something I usually also say when I'm talking to startups. We found a solution for problem XYZ. That's really cool. And this is also something that our researchers are prone to, finding cool solutions for problems that nobody has, or giving answers to questions nobody has. In times of scarce resources, I find it really important to remind ourselves every time we are talking about research, and especially buzzword-related research like artificial intelligence, that things should serve a purpose. And now I want to show you the curious case of the river salmon. I don't know if you have seen on the left hand of the screen, you probably, if you Twitter user, it was in the good old times before Elon Musk entered the stage, although he entered the stage a few months ago, but before he bought Twitter, you probably saw that on Twitter. We have here 4 shots of salmon swimming in the river, and this is obviously an AI engine generated set of pictures. And the general consensus when you are looking into the discussions on Reddit and on Twitter is we are all doomed. If artificial intelligence answer to the question of salmon in the rivers, we can probably pack our things in. And one of the more reasonable explanations probably was flawed training data. You get the answer on the question you have asked, and you get the results from the training data you provided to your models. So garbage in, garbage out is one of the comments which pretty nicely wrapped it up in the discussion. But doesn't that sound a little bit fishy to you? Actually, when you're looking a bit closer into it, I just toyed a bit around with stable diffusion, and bear with me, I know that image generation is not the same as hydrology, but I think it's something which is pretty, well, it's visual and it's easy to understand. If you enter the phrase salmon swimming down a river, as it was obviously done with the 4 pictures we saw before, what I got was 4 salmons. The AI engine took some liberty in coloring the salmon. It's pretty pink, but it's fish. So that's correct. If you enter salmon fillets swimming down a river, you get pictures which are very much like the ones we saw in the original post. So what happened here? Obviously, somebody pulled a prank. But nobody actually, when you look into the discussion, nobody actually came up with the question whether this is real or not. Everybody discussed about how AI is stupid, how AI is dangerous, how AI is going to ruin us. So my 3 takeaways from this little discussion in the social media is, if things look wrong, they probably are. You have to ask the right questions to get the right answers, and people hate AIs. And this is something which is really important when we are talking about how we can build systems which help people live in situations which are due to the fact of scarce resources, due to the fact of growing cities, due to the fact of heavy rain situations and all other developments. People actually are afraid of not knowing, first of all, what's going on, and not knowing how the problems are going to be solved. The black box problem of AI is something which I would ask you, please, in all discussions you have, to keep in mind, because everything we do needs to be accepted by the people we do it for. Well, actually, obviously not everything, but in an ideal world, I would love to have people have an understanding not of how ML works, but have an understanding of how we come to a result. And to be honest, a lot of times we get a result from a machine learning model. We're actually not sure how it reached that decision, or it came to that result ourselves. And 3 suggestions when we are talking about artificial intelligence. First of all, keep an open mind. That's a reference to the question of probably something looks fishy, it is fishy, or not a fish in this case. Build things to empower people. When I mentioned the asking right questions point, have in mind that people who might be using the applications you are developing are not researchers, they are not data scientists. They are people who are working in the public administration, for example, who want to get help in their everyday business using the applications you develop. You should have in mind that you have a great model, you have great theory, but what you build must be usable. It must empower people to work with it and not lead them to ask the wrong questions. And last point, finally, trust requires openness. So this nicely circles back to my introduction. Openness is something which helps people to understand what's going around, but also helps to build better solutions. People usually have a pretty good idea of what is happening around them, and they sometimes have pretty cool ideas how to enhance things. And if they know what's going on, they will be able to rely on what you're offering them. So keep in mind a little bit of openness, and looking on our timetable, as we are, I think, 8 minutes over our time, I will just close my keynote at this point. If you want to discuss anything with me, join me on Twitter or anywhere else, as long as we can be on Twitter. As long as it's socially acceptable to be on Twitter, you can reach me there. And thank you very much for listening.
Thank you very much, Nicolas Zimmer. Yes, let's still be on Twitter as long as we can still use it. And if you're there today, make sure you're using the hashtag #BluePlanet to tag us there. Since I have you both here, thank you so much for joining. And I've got a question for each of you, if you can stick around for another minute. I know we are a little bit behind schedule, but I think everyone out there listening, they like what they hear, but they have a couple of questions. And one of them, I'll start with you, please, Nicolas Zimmer. So we're looking at how administrations and large tech companies, Google, for an example, can perhaps even cooperate as we're looking at AI and ML and the water industry. What do administrations need to do to ensure an adequate level of security and privacy? Openness is great, but how do we take care of those issues?
Yeah, I mean, it's first of all, it's data protection, obviously. This is something which is a very strong tradition in Germany, and people are always saying we have too much data protection. To be honest, I don't think that we have too much data protection. Nobody has yet shown me something he or she wasn't able to build sticking to the rules. Probably it's a little bit harder to do so. But when it comes to the question of making sure that data protection rules are also followed, when we are talking about working together with Google or with, well, let's talk about others, Amazon, who are also in the smart cities sphere, or Siemens or whoever, we need data governance models, which are setting out clear rules about how we cooperate, what data we share, and what anonymity level we are providing. So when we are, this is another aspect of openness, actually. When you have open and clear rules and everybody knows what to do and everybody knows what is done, then I think data protection is something which is really feasible.
Thank you so much for your response. Sella Nevo, I want to come right to you. I want to tie in what Nicolas Zimmer said. He said, these 3 challenges, and the third one was people hate AI. I know that the flood forecasting system, it's active in India and Bangladesh, and you want to expand it to other areas and regions. But how do you ensure that even if people hate AI, that people still participate, that citizens and local governments still say, sure, we'll try this out?
Yeah, so first of all, so we've just in the past few months expanded to 18 new countries. So we're now in quite a few different countries, and I think that I think you sometimes see extreme reactions in both directions. So sometimes people hate AI, and sometimes we've also had sometimes conversations with the governments where we were trying to present them the accuracy of our systems, and they were like, okay, but do they use AI? Okay, then we want them, and so. Neither of those extremes is correct. And I very much agree with what Nicolas said earlier, where really the question is, what value does it bring, right? So at a professional setting, it's useful to talk about progress and advances and so on. But really the question is, what do we get out of it? And I think that really there really has been quite a revolution in the last few years where both the difference in the actual quality and performance and robustness is large enough that I think to convince more people. And I think it's also becoming more and more of a consensus. A few years ago, the papers that I showed, some of them existed a few years ago, but if you asked most hydrologists, again, public sector, academia, they'd be like, I don't know, all this machine learning stuff. I think that is slowly changing. So long story short, I think through a lot of conversations, some of them in academia, some of them in industry, some of them in the public sector, but really what I think AI systems need to show is, the burden is on us. We need to show results in papers, but also in the real world. And I think we're making that progress. And so I'm pretty optimistic that we're going to have a good pace of more and more governments kind of taking this on.
Thanks so much. Thank you to both of you so much for joining us today. Sella Nevo, the head of the Google Flood Forecasting Initiative, and Nicolas Zimmer, the CEO of the Technology Foundation, Berlin.